This lecture will focus on the period of a spring and the period of a pendulum. It turns out the period of oscillating spring is dependent only on the mass applied to it and its stiffness. Changing the amplitude will not change its period or frequency. The period T is 2 pi times the square root of the mass divided by the spring constant. A 200-gram mass is placed on a spring that has a spring constant of 20 newtons per meter. What is the period of the spring? Plugging into the period formula, we find that the period is 2 pi times 0.200 kilograms divided by 9.8 meters per second squared, raised to the 1/2. This gives us an answer of 0.90 seconds. What happens to the period if the mass is doubled? What happens to the frequency? If the mass is doubled, then the period will go up. Since period is inversely related to frequency, the frequency would decrease. A simple pendulum is another common example of a simple harmonic oscillator. A simple pendulum consists of a mass M of negligible size suspended by a string or rod of length L, a negligible mass. The angle it makes with the vertical varies with time as a sine or cosine. The position, velocity, and accelerator formulas are the same for any oscillator. Looking at the forces on the pendulum bob, we see that the restoring force is proportional to the sine of the angle, whereas the restoring force for a spring is proportional to the displacement, which is just the angle in this case. Since every mass falls at the same rate g on Earth, then the period has to depend on gravity, but be independent of mass. We can treat the pendulum like in an identical mathematical way to that of a spring. Therefore, we find that the period of a pendulum depends only on the length of the string and gravity. The period of the pendulum, T equals 2 pi times the square root of L over G. This means that the longer the pendulum, the longer the period, and the bigger G is, then the shorter the period. What is the period of a 2-meter-long pendulum on Earth, where G is equal to 10 meters per second squared, and on the Moon, where G is 1.6 meters per second squared? Using our formulas, on Earth, the period would be 0.26 seconds, and on Moon, the period would be 9.8 seconds. Note that the mass makes no difference. There is no mass in the equation, so this would be the period on each planet regardless of the mass hanging on the pendulum.